I want you to imagine a situation where we have a box with 16 M&Ms. 8 of these M&Ms are green, 5 are yellow, and the rest are red. Of course, since we have 16, that means 3 are left to be red. And we want to know when we select any 3 at a time, what is the probability that exactly 2 of them are yellow? So we reach into this box and we pull out 3 M&Ms. We want to know what the probability is that exactly 2 of them are yellow. So this question is really similar to the binomial distribution we saw in the last video. In this case, our population, or our total set consists of 16 M&Ms. Our success, or what we're interested in this case, is pulling a yellow M&M. And since we have 5 yellow M&Ms and a 16 total, the chance for the first M&M to be yellow is 5 out of 16. Our failure in this case is pulling a green or red M&M, anything that's not yellow. And of course, our failure is 1 minus our chance of success, which is 11 out of 16, or it's simply 8 plus 3 divided by 16, which is 11 out of 16. Now the only problem is that we're selecting 3 at a time. So we have a non-replacement situation. And the way you can look at this is that since we're selecting 3 at a time, this is the same thing as saying select 3 individually, but don't place them back. So if we look at simply pulling a yellow M&M, on our first trial, if we do pull a yellow M&M, the chance that we pull it is 5 out of 16. Since we have 5 yellow M&Ms and 16 total M&Ms, the chance that we pull a yellow is 5 out of 16. On the second trial, the chance that we pull a yellow M&M is going to be 4 yellow M&Ms left and 15 total M&Ms left since we pulled out a yellow one. So we have 4 yellow left and 15 total left, so the second chance is 4 out of 15. And then the third chance would be 3 out of 14, and so on. And so your chance at success and chance at failure changes between trials. And so this situation is not binomial. Since we said earlier, or in the last video, that for a experiment to be binomial, these chances of success, or P, and the chance of failure, or Q, needs to remain consistent between successive trials. And over here we can see that that's not the case. So the way to properly answer this question is to employ the hypergeometric distribution. Now this distribution occurs when we have a total population, or a set of n elements. So we have n elements total. So in this case, our total elements is 16 M&Ms. And we have m of these elements to be successes. So in this case, we're interested in pulling yellow M&Ms. So 5 elements from our total elements are considered to be successes. Finally, our experiment has lowercase n trials. And a trial is, once again, just a repetition of one of your actions. So in this case, we're selecting any 3 elements, or any 3 M&Ms at a time. That's the same thing as saying select 3 individually. So each trial in this case is selecting one M&M. And we select 3 individually without replacement, which means without putting them back. So in this case, n, or lowercase n, is going to be 3. Now the way this distribution is going to work is that we're interested in getting k successes. K successes. So in the question, we're told that we want to calculate the probability that 2 of them are yellow out of the 3. So out of our 3 trials, we want 2 successes. So the probability, P, x in this case is going to equal 2. So P of x is equal to k. We can replace k with 2. So we'll look at this particular example first, and then we'll generalize. P of x is equal to 2 is equal to the ways that we can choose 2 yellow M&Ms from the group of 5 total, and then multiplied by the ways to not pick yellow once, since we have 3 trials. So we want to pick 2 yellows, and then we want to not pick yellow 1 time from a total. We have 8 plus 3 red. So we want to not pick yellow from a population of 11 divided by total ways to pick 3 M&Ms from a population of 16. So if we define x, let x be number of yellow M&Ms chosen. Then if we define what we just did mathematically, we have P of x is equal to 2 equaling 2. We're choosing 2 out of 5 M&Ms. 2 M&Ms must be yellow, and we need to choose those M&Ms from a set of 5 total yellow M&Ms. So we have 5, choose 2. Multiplied, we need 1 non-yellow M&M, and we have a set of 11, since 8 are green and 3 are red. So 11, choose 1, divided by the total ways to choose 3 M&Ms from a set of 16. So 16, choose 3. And the answer we'll get here is 5 choose 2 is 10. 11 choose 1 is simply 11. And 16 choose 3 is 560. And so our final answer reduces down to simply 11 out of 56. So the probability when choosing any 3 M&Ms from this set of 16 at a time, the probability that 2 of them is yellow is 11 out of 16. And that's the same thing as saying when we pick 3 M&Ms 1 at a time without placing them back in, the probability that 2 of those M&Ms are yellow is 11 out of 16. Now if we want to generalize, we have P of x is equal to k. So now we have k successes. That will equal, we have our total set of successes and we're pulling k out of them. So our total population of successes, if you remember, was m. And we're choosing k out of them, since that's how many successes we're going to get in our sample. Then from the remaining population, in this case our total population was n. So the remaining population is n minus m. That's going to be the remaining population that is not a success. From that remaining population, we're going to choose, recall that we had n trials, so we had lowercase n trials. K of those trials were successes, so the remaining trials is going to be n minus k. So we're going to choose n minus k to be non-successes. And then we're going to divide by the total number of ways from our total set to pick n elements. And the more common way that this is written, since it kind of looks messy here, it's just a jumble of letters. And the second way is also a jumble of letters, but it's a bit more organized, is using the binomial coefficient notation. So you have m, pick k. So that's going to represent your successes, multiplied by the number of ways to get some failures. So n minus m is your population size for your failures, and you're going to pick n minus k of them to fill up your remaining trials. So these are failures, divided by the total number of ways to pick lowercase n elements. And that's going to be your hypergeometric distribution. So now we're ready for an example. We have 11 people in a class that are soccer fans. The class consists of 31 students in total, and we select 7 for an interview. And we want to know the probability that less than 6 of the ones we selected like soccer. So if we define our random variable, we're going to say let x be the number of students selected that are soccer fans. Then in this case, the answer that we're looking for is what is the probability that x is less than 6. And since x is a discrete variable, we're dealing with people, and you can only have integer amounts of people, 1, 2, 3, 4, and so on. You can't have half a person. Then the probability that x is less than 6 is the same thing as saying the probability that x is equal to 5 or less than 5. And that's the same thing as saying x is either equal to 0, 1, or 2, or 3, all the way up to 5. And these are all OR situations, so we're going to add them. So the probability of 1 plus 2 plus 3 plus 4 plus 5. Now normally, once we get to this step, we'd have to do the hypergeometric distribution for each one of these. So we'd have to perform the hypergeometric distribution 5 times, add them all up, and that would be our answer. But that's a lengthy calculation and it wastes a lot of time. So what we can realize is that if we consider our entire sample space, or all the possibilities in these selections, we're going to have 7. So the sample space in this case, or we're going to have 8 rather. So our sample space, the probability over here is going to equal 1, since it's all the possibilities that can occur. It's going to equal the probability that 0 of those selected are soccer fans, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. So that encompasses all the possible outcomes in our experiment, and so if we add all these probabilities together, we'll get 1. We want to figure out what this equals. So we're looking for, or we forgot over here to add p of 0, since that's also less than 5. So we're looking to what all of this equals. So if we isolate over here, for this entire portion, we find that it equals 1 minus p of 6 minus p of 7. So instead of performing 6 calculations, we can perform 2, subtract that from 1, and we'll get the same answer. Another way to put this is that the probability that x is less than or equal to 5 is equal to 1 minus the probability that x is greater than 5. And there's a very important concept that we'll get back to later, but for now, the way you can understand this best is if we draw a graph and we imagine each one of our possibilities having a probability equal to its area. So let's say the probability over here was 1/10. The width of this rectangle is going to be 1, since, for example, over here we'd have 0, 1, 2, 3, and so on. So the width of this rectangle is going to be 1. The height of the rectangle is going to be the probability of selecting the amount of people that like soccer corresponding to that random variable. So if this was 3 over here, the height of this rectangle would be corresponding to the probability that out of the 7, 3 like soccer. So if we continue with these rectangles, and we have 1, 2, 3, 4, 5, 6, 7, 8 total rectangles. Let's suppose this is our number 6. Then the area of all these rectangles is essentially the probability of all the outcomes, and so the total area is equal to 1. And so if we want to find the probability in blue, then all we have to do is take 1 and subtract the probability in red. Once we get rid of that, we're left with what is in blue, which is what we're after. The probability that x is less than 6. So 6 is over here, probability that x is less than 6. Now to actually perform the calculation, 1 minus the probability that x is greater than 5 is 1 minus probability that x is equal to 6 minus probability that x is equal to 7. If we expand this even more using the hypergeometric distribution, we get 1 minus the probability that 6 of the students like soccer out of the 7 is the chance that from 11 that like soccer, we choose 6, multiplied from the remaining 20 students, we choose 1 that does not like soccer, divided by all the possible ways that we can choose 7 students from the total class of 31, or 7 students. So that's the probability corresponding to p x is equal to 6, minus, in order to have 7, from our set of 11 people that like soccer, we have to choose 7. From the remaining 20, we're choosing none of them, divided by, we have a total class of 31, and so the total ways that we can pick is 31, choose 7. And if you plug this into your calculator, you'll get 1 minus 616 over 175, 305, minus 72 over 175, 305, which is equal to 6,023 divided by, or actually instead of writing that at this point, you simply jump to the decimal. It's equal to 0.9964. So the probability that 6 or less of them like soccer is pretty high, and it's 0.9964.